Hey guys, today we are doing depletion of the stratospheric ozone layer. We are going to talk about both types of ozone, and we're going to talk about, and we're going to talk about specifically what gases deplete the ozone layer and why that's bad. So just to review real quick, here are your different layers of the atmosphere. We've already talked about this, but the layer that's closest to us, where we live, where the weather is your troposphere. And then once you start transitioning into the second layer of the stratosphere, we call that the stratopause. And then you have your stratosphere. Ozone layer is in the stratosphere. And then the third layer is the mesosphere. And then the top layer is the thermosphere. Okay, and then we see that again here. Troposphere, stratosphere, here's your ozone layer, and then the mesosphere. So the main things we're going to be talking about today are troposphere and stratosphere. We need to remember troposphere is where we live. Ozone in the troposphere is generally bad. Stratosphere is the second layer. That's where the ozone layer is found. That's the protective ozone layer. We need it, and we're getting ready to talk about why it's so important. Okay, so as we just said, ozone in the troposphere where we live is very, very bad. It's actually a greenhouse gas, and it's what we also know as smog. Okay, so just to review how ozone in the troposphere would be formed, you would have nitrogen oxide that's given off when we burn fossil fuels. That's going to react with oxygen to form NO2. And again, that's going to create this brown, hazy gas in the air. And then also when NO2 combines with sunlight, it can break up into plain NOs, nitric oxides, and singleton little oxygens. Whenever you get little singleton oxygens, that's always bad news because single oxygens can join up with O2. And when you have a single oxygen that can join up to O2, that forms O3, which is ozone. So it's kind of a complex reaction, but if you eventually build up to NO2 and then you can break it apart with sunlight and you get little O's by themselves, if an O joins to O2, you get O3. And again, O3 in the troposphere where we live is bad. That's smog. We said that usually happens in the afternoon when the sun's really bad in cities. Okay, so then if the tropospheric ozone is really bad, stratospheric ozone is really good. And the stratospheric ozone is the type of ozone that provides us with that protective ozone layer up in the stratosphere. And so here's one more reminder that stratospheric ozone is good, tropospheric ozone is bad. This is what ozone looks like. Triple O, okay, 3 oxygens bonded together. Here's a little bit better picture. And this kind of shows you how ozone is constantly being produced and destroyed, and usually the production and destruction of ozone happens at normal levels, but today we'll talk about why the depletion of it is bad. It's actually being destroyed faster than it's being created. Okay, sunlight has a lot to be involved with our stuff that we talk about today. When UV radiation comes in, it can actually split apart oxygens. And remember, we said whenever you get a little singleton oxygen, it can bind to O2 to make oxygen. So it's a natural process to continually create ozone and to destroy ozone. Here's a graphic reminding us of the incoming or the fate of incoming radiation. We've talked about this a million times by now, but we'll just go over it one more time, and you're actually going to talk about it with climate change here in your next notes. So here you can see out of all of the incoming UV radiation, you can have a certain percentage of it is absorbed by the atmosphere, some is absorbed by clouds, some is reflected back by clouds, some is reflected back by the surface, and some is actually absorbed by Earth's surface. And then we're going to talk more about this in your next notes. Eventually, any radiation that makes it down to the surface will be re-radiated back out by the surface of the planet in these long, big wavelengths called, that's bad, called infrared wavelengths. And that's what leads to the greenhouse effect. Okay, this graphic is super, 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 super important. I think you actually have it on your notes. This is huge. This is where we said having a background in chemistry is very important because you have to know this reaction, you have to be able to write it out, and you have to be able to understand it. What this reaction is showing us how CFCs will break down ozone. And actually, before I get to that, let me go to the next slide so we can see an explanation of that, and then we'll come back and talk about what actually happens. So we just talked about how the stratospheric ozone is the important ozone layer. What types of things are breaking down this important ozone layer? Well, one of our main culprits is what we call CFCs. CFCs are chlorofluorocarbons. They're chlorofluorocarbons because they contain a carbon in the middle, some fluorines, and some chlorines. Okay, chlorofluorocarbons, CFCs. And as we can see here, ozone is O3. It's naturally produced and destroyed by oxygen atoms being split by UV radiation from the sun. That's the picture we looked at earlier. And normally we said this process is balanced. Okay, normally just as many that are being made are being destroyed. However, when UV radiation comes in and hits a CFC molecule, it also works on this molecule. And when it does that, it can break off the chlorine. And that's really bad news, because the chlorine is really, really strongly attracted to O3. It really, really strongly wants to bond with an oxygen, with a single oxygen. So what it's going to do is that Cl is going to find an oxygen in the O3. It's going to bind to the oxygen. And when that happens, it's going to turn O3 back into an O2. And so the Cl is going to pair with the oxygen. So let me show you what that looks like. Okay, here's your CFC. Carbon. I believe the greens are the chlorines, so 1, 2, 3 chlorines, and then you've got a fluorine as well. First thing that happens in this little reaction is UV radiation is going to come in. UV radiation is going to knock off that single chlorine atom. And as we said, that single chlorine atom is dangerous because now it wants nothing more than to go and find an oxygen to bind with. And so it'll probably run into an O3, an ozone molecule. And when it does, it's going to rip away one of those oxygens. So chlorine is going to come in. It's going to steal one of these oxygens. That's going to turn this into ClO. This then becomes just an O2 instead of O3. And O2 is just regular oxygen, so that's fine. It's going to be up in the atmosphere. But what's dangerous is this combo right here, because what can then happen to the ClO is if you have another kind of rogue lonely bystander oxygen, that lonely oxygen can come and bind to the ClO oxygen, and it can steal the O back away from the chlorine, so then you make another O2 here. And the reason this is so dangerous is now chlorine is back out on the loose again. And chlorine is very stable. It will remain in the atmosphere for a very, very long time. It can go after thousands and thousands of ozone molecules. So basically, it kind of starts this ongoing process where this one chlorine atom can go and destroy tons and tons of ozone molecules. Okay, so that's a really important reaction to understand. Okay, so this is what we just said. We said the reason that you having that little single chlorine atom by itself is so scary is because it's very stable. It's really going to slow down the rate of ozone reformation, making that the creation, destruction of ozone process very unbalanced, where much, much more is being destroyed than what's being made, because these chlorines can attack lots of ozones. Okay, a little bit more about our very important stratospheric ozone layer. The reason it's so important is because it blocks UV radiation. It blocks UV radiation. Okay, there's 3 different types of UV radiation. The worst one is the UVC radiation. The stratospheric ozone, you can see over here, it actually absorbs all of the UVC, so that's good because that one can do major, major damage. And it partially absorbs. It absorbs most of the UVA and the UVB rays. Okay, so it says 97 to 99% of high frequency UV is blocked by the ozone. So just a little bit of UVB and a little bit of UVA gets past, but even the little bit that does get past does damage to us and to our ecosystems. Okay, so one of the major things we could talk about how UV radiation affects humans, I'm sure you guys are already aware, is with our skin, issues with our skin. So this is kind of a picture. I remember my mother-in-law showed it to me a while ago. It freaked me out. Looking at this girl, she looks like she's got nice, even skin. When they use a special type of camera that shows sun damage, you can see that she's got all sorts of sun damage underneath of her skin. And as you get older, you develop sunspots and that sort of thing. Actually, it looks like we're missing part of that little blurb, so let me see if I can move that up. So it says, okay, this is the type of damage that would happen due to prolonged exposure to the sun's rays, and this type of UV photography is used to kind of help to scare some students into actually putting on sunscreen. And that's one thing that kind of all young people have to kind of go through as they get older. I've always been a fan of laying out in the sun, even going to the tanning beds, and as I've gotten older, I've realized it's just not worth it, especially with skin cancer being so deadly. Okay, and this is all stuff that we've already talked about before, so I'm going to go on there. Okay, what are our major culprits in terms of the gases that deplete the ozone layer? We've already mentioned these guys earlier, your CFCs, chlorofluorocarbons. We've actually seen the reaction of how they attack ozone. Another big one is methyl bromide. It's used in agriculture. It's used as a fumigant or a pesticide. It's used to spray down crops. And we'll come back and talk about that a little bit more later. But yeah, mostly used in agriculture, used as a spray, as a pesticide. And I'm trying to see. We'll come back and get that at the end because I have some more stuff I wanted to tell you about that. And then another example, and there's actually even more examples, is PVC. PVC is like those plastic pipes that you might see underneath of your sinks. PVC is actually just a type of plastic that's used in a lot of different things. So, other things that you would find CFCs in, you would find them in anything that has flame retardants. So like even like some pajamas have that. Really any products that have any kind of flame retardation aspect to them can have CFCs in them. Fire extinguishers, refrigerants. Used to be an aerosol, like any kind of spray can, the propellant they used had CFCs in it. In our country, we haven't had CFCs in spray cans since like the 70s. Okay, yeah, and we said methyl bromide is your fumigant you use in soils to kill pests, pesticide. And a lot of PVCs we see in construction material, but not always. We see in different stuff. Okay, now there is such a thing called an ozone hole. The ozone hole is down by Antarctica, so we're all the way down at the South Pole here. And it says the ability of ozone to reform has created a hole in the ozone layer. This hole is seasonal and cyclic, so we only see it during a certain time of the year, and it is a cyclical thing. And it's not truly a hole. It's just a thinning of the ozone layer, but they call it a hole because instead of it being nice and thick like it normally is, it thins out. So the seasonal time that we see it during the Antarctic spring, which is opposite of our spring. So Antarctic spring would be September to December. Okay, so that's when they have the thinning of the ozone, and it's mostly down here in the southern hemisphere. Now another continent that it affects is Australia. Okay, so Australian people and Australian ecosystems are kind of hit the hardest besides Antarctica by the ozone hole. Okay. Alright, so just going back to ozone in general, it says the ironic thing is that we often have too much ozone on the surface of Earth, meaning in the troposphere. And so again, here you see a chemical reaction of how ozone or smog is formed in the troposphere where we live. Okay, and then when you have ozone down in the troposphere with us, that can lead to lung disease, a decrease in crop productivity, and asthma. And it creates that lovely brown haze that we call smog. Okay, so going back to the ozone hole, why is it bad to have that ozone hole? We're going to go through lots of different reasons for that. First of all, if you have a hole or a thinning in the ozone layer, it's going to allow more UV radiation to come in. More UV radiation is linked to causing mutations in our DNA, especially in your skin cells, which could lead to skin cancer, which is otherwise known as melanoma. If this mutation happens on the gene for cell growth, meaning that there's a gene in your DNA that controls when the cell should divide, if that code is mutated, then your cell doesn't know when to divide, and it keeps dividing, and cancer can develop. You get a tumor. Okay. Now, we're exposed to mutations all the time, or sorry, we're exposed to like mutagens all the time, and we do acquire mutations a lot, but our cells usually can fix those. So a lot of times when we get mutations, they are repaired and they go unnoticed. I think they say every person harbors like thousands of mutations, and they get repaired, and it's not a big deal. However, if the cell is able to replicate the DNA before it repairs, then that messed up DNA can get passed on to other cells, and that's how it could be kind of like a almost like a positive cycle there. So this shows incoming UV radiation. This shows something that a common mutation that would happen from incoming UV radiation. It's where two thymines get stuck together. So that's just one type of mutation. Okay, so melanin, you guys probably talked about this term melanin in biology. Melanin is your pigment. You have pigment in all sorts of body parts, your skin, eyes, hair, but the melanin we're going to talk about today is the pigment in your skin. That's what gives you your skin color. Some people are born with, they don't have genes to make much melanin, and then other people have darker skin and they make a lot of melanin. So this melanin pigment is contained in your epidermis, and the job of melanin, the job of your skin color, of your pigment, is to absorb UV rays, and then it also makes a special vitamin D. Now, it gets a little bit unfair here because if you are naturally, you have a nice darker skin color, or you can produce a nice tan when you're exposed to the sun, you naturally have a greater buildup to protect you from the sun. Okay, so if you have dark skin all year long, they say that you basically have like a built-in SPF 25. So you always have sun protection. Doesn't mean that you shouldn't wear more, but you always have a built-in protection more than a fair-skinned person. If you are fair-skinned and you really never get color and you just get burnt, you do not produce much melanin, and you are at very, very high risk to get burnt and then to be exposed to possibly developing mutations. So you have to be very, very careful with your exposure to the sun and your exposure to UV radiation. So here it says the less melanin you have, the more UV radiation will actually reach your dermis, which could then lead to a burn. And then again, they say that your incidence of burns and blisters that you had in your life could show an increased risk of skin cancer later on down the road. Okay, how do you recognize that you have melanoma or skin cancer? You want to check moles, okay? And you've probably heard about the A, B, C, Ds of your moles. A stands for asymmetry, so you would make sure that your mole is symmetrical, which it doesn't look like any of these moles are really symmetrical. This is really the only one that's kind of symmetrical. And by symmetrical, we mean like it looks the same on both sides of it. B is border. You don't want the border to be all kind of jagged like this. You want it to be a nice smooth border. C is color. You don't want it to be especially dark. You don't want it to be like a blue or a weird color. A lot of these have a lot of variation of color in them, so they show bad signs of possibly being melanoma. And then D is diameter. You don't want it to be any larger than the size of a pencil eraser. So you're supposed to do mole checks on yourself. You're also supposed to go to a dermatologist and have a dermatologist do a mole check on you. I've been to a dermatologist twice where they've done the mole checks, and they actually, this past fall, they removed 4 moles. One of them was actually precancerous, so that's pretty scary. So it's really good just to be safer than to be sorry, because melanoma is one of the most easily treatable forms of cancer if you catch it early. The way you treat it is you remove the mole. You get rid of that cancer. If you have a mole and it's cancerous and it stays on your body, it can progress to stage 3 and 4, where the cancer can actually spread to other parts of your body. And they say it's one of the most deadly forms of cancer once it does progress to a malignant stage. So that's my public service announcement for the day. Make sure you get your moles checked. Go to a dermatologist if you think that you have any weird moles, and they will remove them. And basically, you don't have to worry about those moles anymore. Okay, so why else is having a hole in the ozone layer a bad thing? It affects ecosystems. It affects living things. Here's what they saw in a school outing in the 90s. This is down in Australia where they found these frogs. They're all mutated. They found a lot of the frogs' eggs weren't even hatching. So what's going on here is amphibians are often indicator species. They don't have hair. They don't have thick, leathery skin. They don't have hard eggs like other things. They have the soft eggs, and they the gelatin type eggs, and they have the moist skin. So they absorb a lot through their skin and into their eggs. So they're often the first things to be affected when something goes wrong in an ecosystem. So again, we call those indicator species. Okay, so when we start noticing stuff is going kind of wonky with the frogs and the amphibians, then we know that other life forms are probably going to start being affected pretty soon after that. Okay. What about productivity, meaning like with your plankton and with your plants? Okay, so plankton in the water, there's two different ways they can respond. So the first one says here that a natural protective response is to produce more light absorbing pigment, but this isn't actually triggered by the dangerous UV rays. And so we said UVB. UVB can be pretty dangerous. It says UVB, for some reason, it does not trigger plankton to make more pigment, like would sometimes happen with other forms of UV. So it will not acquire extra protection. So this is actually bad. Number two, it says also plankton might sink lower into the ocean if it becomes brighter, too much UV radiation shining down on it. The plankton would actually sink lower in the ocean, which would reduce the amount of light that it receives, which would reduce the rate of photosynthesis, which would reduce the amount of productivity, which would then affect the entire ecosystem because the ecosystem is used to living off of a certain amount of plant matter. And so if that decreases, that would affect the entire ecosystem. Okay. And this little graphic real quick, it just shows you how much the CFC concentration has increased since the 1950s. So it has gone from nothing to close to 0.3 parts per billion. Okay. So here's some other effects that having increased UV radiation would have on ecosystems. Here you have decrease in agricultural yields and a decrease in overall forest productivity. So not just plankton, but land plants would have decreased productivity from really strong amounts of UV radiation. Okay, again, DNA damage, mutations to fish larvae, plankton, organisms at the bottom of the food web, which would then affect higher trophic levels in your food web. Increase in the rate of skin cancer. We already talked about that. Now, I do have a little statistic here about Australians, if I can find it. Where is it? I think it is here. Nope, it's not in this one. I'll see if I can find it in a moment. But Australians are very susceptible. There's some statistic that it's like 1 in like 3 or 4 Australians are thought to probably develop cancer at some point of their lives because they're down there near that UV hole. Oh, here it is. 2 out of 3 Australians will probably most likely develop skin cancer. And then Australia, they actually offer free cancer checks at the beaches just because they're so paranoid and they're always making sure that people are being aware of what they're doing to themselves when they're laying out at the beaches. And then when they have their morning weather announced to them, they also announce the UVB levels. So UV is a big part of Australians every day. And the incidence of melanoma in our country has even increased a whole bunch. It says in America in 1935, the chance of developing malignant melanoma was 1 in 1,500. Today it's 1 in 75. So that's increased a lot. It's because people are sunbathing and going to the tanning beds. They're being a lot more careless with that kind of thing. Okay. Increase in xeroderma pigmentosum. That is a genetic disorder where people are born where they're allergic to the sun. They cannot go out in the sun at all. They can really only come out at night. It's actually very sad because if they come out in the sun at all, they get severe, severe, severe burns. So it's a pretty interesting genetic disorder. If you're interested in it, you can look it up. There's some pretty nasty pictures out there, but it's very sad because, like I said, they have to cover themselves up completely. They cannot come out in the sun. They also expect an increase in cataracts and changes in your eyes, like in your retina. So it says a lot of livestock in Argentina and Chile are already suffering from increasing cataracts. Animals and then also humans too. And then it also suppresses immune system responses in us and animals. Okay, so what can we find CFCs in? I've talked about this a little bit. Aerosol sprays, although we have not seen them in aerosol cans since the 1970s in our country. That is no longer, but we used to see it especially in spray cans. Certain kinds of cleaning fluids, freezers and refrigerators have CFCs, air conditioning units, industrial solvents, dehumidifiers, and then foam insulation. And again, a lot of this foam insulation is you need a propellant to kind of spray it, like in your house if you have had new construction and you see them spray that foam. It's probably the propellant. Then we have an alternative called HCFCs. We'll talk about that in a moment. It's not quite as bad as CFCs, but you'd find these in heat pumps and air conditioners. And so where are we at in terms of history with this issue of ozone depletion? In 78, U.S. banned CFCs in those propellants and those spray cans. So we haven't had CFCs in spray cans since the 70s. In the 80s, we developed the Montreal Protocol. It's going to be very important. We'll talk about that more here in a little bit. Major law that was enacted. It was an international law. It's considered to be extremely successful. It's considered to be one of the most successful international environmental agreements to date because a lot of people cooperated. So here we have some information about that. It says it was an international conference to control these CFC chemicals. It was signed by us and 22 other countries, and the idea was to limit the production and use of CFCs. Once we signed it, there was a 50% reduction in CFC production worldwide by the year 2000. It's now been signed over 90 nations. And then it was revised to require the virtual phase out of CFC production by 1996 because some countries are still using them. We'll get to that in a moment. And then in 1990, we have the Clean Air Act Amendment, which we've already been talking about, and that has a whole component on ozone depletion. Now, something kind of interesting here with this protocol, and we'll talk about this with other laws too, is that there's a little addendum that says that your less economically developed countries are still allowed to use and make CFCs because they're developing, they're industrializing, so we kind of give them privileges that other countries don't have. But then also they say that there's still an illegal trade of ozone depleting substances across borders as well. So they're not completely phased out, but we want to get them phased out. Okay, so what are some methods for reducing the manufacture and release of these ozone depleting substances? Really importantly is to recycle items that have the CFCs in them. Don't just take your old refrigerators or AC units to the landfill, because if you just dump them in the landfill, that's going to leak CFCs out into the ecosystem. So they have to be carefully controlled. An idea is to put in legislation to have to return these types of things to the manufacturer, so the manufacturers are responsible for disposing of them properly. Using alternatives to gas-blown plastics, PVC, so using other types of construction materials. Using alternative propellants. So again, we don't use CFC in the propellant spray cans anymore, so maybe using CO2 gas instead, propane or air. And then using alternatives to methyl bromide, which we said is that fumigant pesticide that you use in the soil. The downside to a lot of the other fumigants that they use is that most of the alternatives they use are actually greenhouse gases. So which problem do we want to fight here? Do we want to fight greenhouse gas problem, or do we want to fight the ozone depletion problem? Okay, so what are some ideas for alternatives and replacements for CFCs? We've already mentioned this briefly, but you have what's called HCFCs, which is hydrochlorofluorocarbons. There we go. The pros here is that they break down more quickly in the atmosphere. They don't last for decades and decades like the chlorines do from the CFCs. So they're not going to have as long-lasting effect as your CFCs. The negative aspect is that if they're overused, they could cause damage to the ozone layer in the same way as CFCs. And it says redesigned appliances could use more energy than the original model. So if you have appliances that are now using these in place of CFCs, they might actually use more energy. So now we're contributing to other environmental issues. Second alternative is called an HFC, hydrofluorocarbons. Positive aspect here is that they do not contain chlorine and are therefore safe for the ozone layer, so they don't have that creepy chlorine that stays up there and messes up all sorts of ozone. Negative aspect is that you have safety questions like, is it too flammable? Is it toxic? We don't know. Hydrocarbons would be just like, well, methane is a hydrocarbon, but some other hydrocarbons are butane, propane. It's just carbons and hydrogens. Positive aspect is that they are relatively cheap and readily available. Negative aspect here is that they're probably pretty flammable, and they could be poisonous, and some could even increase pollution at the ground level. Ammonia is a replacement. Positive aspect, again, it's a simple alternative for refrigerators, using it as a refrigerant instead of CFCs. Negative aspect is that it must be handled carefully because it is a toxic caustic chemical. And the last one here we have is just plain old water or steam. And the positive aspect is that it's effective for some cleaning applications. Let me see if I can move this guy. Oh, and then we don't have a negative there. Okay, cool. All right, well, that is it for these notes. Let me make sure there wasn't anything else down there. Yeah, I guess there wasn't anything there. So yeah, really important. Make sure that you understand the Montreal Protocol. Very successful protocol, international agreement at this point. Again, they think it's one of the more successful international environmental agreements that we've had. Everybody's getting along. All the countries that have ratified it are cutting their CFC use. What's our status today? Since today the ozone hole is not increasing or decreasing. It's expected to make a recovery to like pre-1980 levels by the middle of the century. So it is getting better. It's improving. This is not one of those doom and gloom, like everything's getting worse. This is actually an environmental issue where we're actually seeing progress with it because we've come together and we are reducing the use of these CFCs. Okay, so that is it for now. And the next notes will be on climate change.